Math 8, Unit 2, Transformations, Lesson 7, Part 2. Area and perimeter of similar figures. Examples. So, remember from the last video, the perimeters of similar figures. When two figures are similar, the ratio of their perimeters is equal to the ratio of their corresponding lengths. So if I compare the perimeter of triangle ABC to the perimeter of triangle DEF, I will get the same ratio as if I compare AB to DE because they correspond, or if I compare BC to EF because they correspond, or I could compare AC to DF because they correspond. So corresponding side lengths have the same ratio as the perimeter. Find the ratio, red to blue, of the perimeters of the similar rectangles. Okay, the ratio of the perimeters, even though I don't know what the perimeters are, will be the same as the ratio of these side lengths, 4 to 6. So comparing red to blue, the ratio is going to be 4 to 6, or 2 to 3. Oh, they wrote it as a fraction. That's actually good. So the ratio 4 to 6, as you see here, reduces to 2/3. So the ratio of perimeters, red to blue, is 2/3. This means red is 2/3 the size of blue, which actually means if we did a transformation from blue to red, the image size would be 2 and the pre-image size would be 3, giving us a scale factor of 2/3. In this lesson, we're focusing more on just the ratio written out, but you do need to know that for scale factor, image goes on top, pre-image goes on bottom. Find the ratio of perimeters, red to blue. All right, on this one, the red size of 3, or the red side of 3, compares to the blue side of 6. That's a ratio of these two side lengths. Now, we know that the ratio of side lengths is equal to the ratio of perimeters, so the ratio of perimeters is also 3 to 6, or 1/2. What's the ratio of perimeters, red to blue? In this case, the ratio of sides is 64 compared to 24. It's going to have the same ratio as the sides, so the ratio of perimeters is 64 to 24. Reduced, this is 8 to 3, dividing top and bottom by 8. So the ratio of perimeters, red to blue, is 8/3, or 8 to 3. What's the ratio of perimeters, red to blue? Well, the ratio of sides, red to blue, is 31 to 31, or 31 out of 31. That reduces to 1. So the ratio of perimeters here is 1. That just means they're the same. These actually are congruent. Find the ratio of perimeters, red to blue. Well, the perimeter of the red one, we don't know, but we do know that one of the side lengths is 13, and a corresponding side length in the other shape is 7. This gives us a ratio of sides, 13 to 7, and a ratio of perimeters, since it is equal, 13 to 7. Okay, when we're dealing with area, when two figures are similar, the ratio of their areas is equal to the square of the ratio of their corresponding side lengths. So the area of ABC compared to the area of DEF, we could do a comparison of AB to DE because they correspond, and then square it. We could do a comparison of BC to EF and then square it, and it'll be equal to the the area ratio. The area ratio of the areas is also the ratio of AC compared to DF because they correspond, squared. Here's another example of why when we double it, you get 4 of the shapes to fit inside. It works with a triangle. You can see here I've increased the size of the triangle using a scale factor of 2, and this increases the area by a scale factor of 2 squared, 4. And the same thing happens with rectangles. If you increase a rectangle's size by a scale factor of 2, its area increases by the scale factor squared. In this case, 2 times 2, 4. So find the ratio of red to blue of the areas of the similar triangles. Well, the areas are going to be the same as the ratio of the sides. The ratio of the sides is 6 to 10, which by the way is 3/5. It's the same as this ratio squared. So the ratio of the areas is 3/5 squared. 3 squared is 9, 5 squared is 25. So the ratio of areas is 9 to 25. And that's how you'd figure it out. Find the ratio of the sides and then square it to get the ratio of the areas. Let's find the ratio of the areas red to blue here. Well, red to blue side lengths is a ratio of 1/2. The ratio of areas, therefore, is going to be 1/2 squared, which is 1/2 times 1/2, or 1/4. The ratio of areas here is 1/4. That means the red hexagon has 1/4 the area of the blue hexagon. Find the ratio of the areas red to blue. First, we need to find the ratio of the side lengths, which we did this previously. The ratio of side lengths is 8 to 3. The ratio of areas is going to be 8/3 squared, which is 8 squared is 64, and 3 squared is 9. The ratio of areas here is 64 to 9, slightly more than 7 times as much area. Find the ratio of areas red to blue. We start by finding the ratio of side lengths, 31 to 31, which is 1. The ratio of areas is going to be 1 squared. The ratio of areas here is 1, which, since these are congruent shapes and the ratio is 1, it just reminds you that congruent figures have the same area. That shouldn't be a surprise. Find the ratio of areas red to blue. First, the ratio of side lengths is 13 to 7. We need to square that ratio, and we get the ratio of areas 169 to 49. So the ratio of the red shape is 169/49 greater than the ratio or the area of the blue shape. A little bit over 3 times as much. Find the ratio of the areas red to blue. Now here we're not given any particular sides, just the perimeter. Now since the perimeter, the ratio of the perimeters is directly proportional to the ratio of the side lengths, then the ratio of the area is directly proportional to the square of the side lengths. Ergo, the ratio of the perimeters squared is the same as the ratio of the areas. So if I take the ratio of the perimeters, it's 2 to 5. The ratio of the areas is going to be squared of that. So these areas relate with a ratio of 4 to 25. 4 to 25. That means that the red shape has an area that is 4/25, approximately 1/6, the size of the blue shape. The ratio of perimeters here is 3 to 5. Find the value of x. Well, the ratio of perimeters, 3 to 5, is the same as the ratio of side lengths, which would be x to 12. Now, which one of these would be a perimeter of 3, and which one would be perimeter size 5? Well, size 5 would have to be the bigger one. So x is in the bigger shape, and 12 is in the smaller shape. This is set up to find the value of x. Now, we could notice here that to get from one shape to the other, we could multiply by 4. So we could get x equals 20 with that information. If that doesn't stand out to you, you can always do the cross product. And you do arrive at the same answer, x equals 20. The ratio of the similar triangles is 9 to 1. Find the value of x. All right, so the ratio here of 9 to 1 is going to be the same as the ratio between the two shapes. We just have to decide whether to put x or 2.5 on top. Now 9 is a lot bigger, so I think that this shape down here is going to relate to the 9, and this shape over here is going to relate to the 1. So x relates to 2.5. Now if we cross multiply and solve here, 9 times 2.5 would be 22.5. And that equals x. Oh, so that's the answer, 22.5 feet. By the way, the area, it doesn't ask about the area, but the area of the blue figure would be 81 times bigger than the area of the red figure, because 9 squared is 81. A scale factor of 9 gives you an area 81 times bigger. Okay, situation example. 2 swimming pools are similar. Their narrowest corresponding measurements are given. What is the area of the second pool? So we've got a small pool, 10 feet across at its narrowest place, there in the middle. Area of 220 square feet. Then we have a second pool similar to it, 25 feet across at the center. And we need to find its area. All right, I would like to do this problem 2 different ways. Way number 1 is going to be using proportions, and way number 2 using direct variation. Okay, first using proportion. We are told that the ratio of areas is equal to the square of the ratio of sides. We know that the figure that is 10 across has an area of 220. The area that is 25 across, we don't know. Let's use A for the unknown. And we just need to solve this. Before we can cross multiply, we are going to have to square 10 25ths. Well, 10 times 10 is 100. 25 times 25 is 625. And this equals 220 divided by A. Now that it is squared, we can go ahead and do some calculations. Let's go ahead and cross multiply. 100 times A is 100A. 625 times 220 is 137,500. And then I'm going to divide both sides by 100, giving me an area equal to 1,375. Oh, that's a horrible looking 5. And 75 square feet. Okay, that's how you would do it with proportions. This can also be done with direct variation. With direct variation, the new area is equal to the scale factor squared times the old area. We just need to find the scale factor. The scale factor getting from 10 to 25 is the image size, 25, divided by the pre-image size, 10, or 2.5. So the new area, the image area, will equal the scale factor, 2.5, squared, times the original area, 220. Now going to the trusty calculator on this, 2.5 squared times 220 gives us an area of the image to be 1,375 square feet, which through this different method is still the exact same answer. So we have, through proportional reasoning, 2 different methods we can use on this problem, using a proportion or using direct variation. Okay, on the assignment, let's take a look at a few of these. Number 1, determine the ratio of perimeters and the ratio of areas in each set of figures. Express ratios as reduced fractions, red compared to blue. All right, so the ratio of perimeters, let's go ahead and do A here. The ratio for perimeters, red to blue, is just going to be 11 to 6. And we're done. The ratio of areas is going to be 11 squared, 121, to 6 squared, 36. So the ratio of perimeters on red to blue is 11 to 6, and the ratio of areas, we square those, it's 121 to 36. On number 2, you're going to be doing a couple of situation problems dealing with area or perimeter. You're going to need to identify information that you can use to set up the problem. And number 3 deals with the same type of thing. Find the areas of both circles. Round areas to the nearest tenth. Compare the areas. What do you notice? Remember to find the area of a circle. Area equals pi times radius squared. And then you're going to compare these. Now radius 1's 9. So you know that'll be pi times 9 squared. And radius 2 is 36. That's pi times 36 squared. That's kind of what you're looking at doing there. And then round to the nearest tenth and then compare. Number 4, you're going to solve each equation. Okay, nice review. Number 5, find each sum or difference. So that's adding and subtracting fractions. Number 6, you're dividing fractions. That's a good review. Number 7, we've got an amusement park and we've got a scale model of a merry-go-round. So actually, I think that's called a carousel. But anyway, you're trying to find the scale of the base area and then use that to answer a question. And then number 8 is to extend your knowledge into the third dimension. Similar solids apply the same principle as do perimeter and area in similar figures. If the ratio of side lengths in a solid is a to b, then the ratio of the surface areas is a squared to b squared. And the ratio of the volumes, a cubed to b cubed. Use this property of similar solids to determine the unknown surface area and volume of the second solids. Round answers to the nearest tenth if necessary. So on this, you're going to, for area, surface area, you're going to want to compare the side lengths. Let's compare blue to red. It doesn't really matter. 4 to 6. And to do it with surface area, area is a two-dimensional thing. It needs squared. And then you're going to compare the surface area, 66 of the blue, to x in the red. And then when you get to volume, you're going to want to compare the same thing, 4 to 6, but this time three-dimensional, so cubed. And then you're going to compare the volume, 36, to, let's use y so we don't have to use x. So you'll solve both of those. Now, remember, there was a second way this could be done. If you know the scale factor is multiplying by 1.5, then you can take, for surface area, the original area and multiply it by 1.5 squared. Or for the volume, you can take the original volume and multiply it by 1.5 to the third power.